Well, thank you for coming to this workshop. This is called Developing Resilient Detections with Obfuscation and Evasion in Mind. My name is Daniel Bohannon. I'm a principal security researcher, currently working at a cloud and identity security startup company called Permiso. I'll explain a little more of my background in the next slide. But yeah, here's my contact information: Twitter, LinkedIn. Most of my projects are on my personal GitHub, and then also there's a blog. There's not many blogs, but it has a list of all of my research or presentations if any of these tools are interesting for you. But feel free to reach out at any point on social media, and I'll be happy to answer. A little bit about me. I've been in the IT industry for 14 years, the last 12 years in full-time security. Studied computer science for my bachelor's degree, and then master's in information security from Georgia Tech. My first 5 years I spent working at the largest fried chicken restaurant company in the US, where I live. I spent 5 years there on their database server team, and then moved into their incident response team after finishing my master's degree. Then I spent 5 years at Mandiant doing incident response consulting. That's where I became involved with researching obfuscation and evasion and writing detections. In 2016, my coworkers encouraged me to present some of the weird things I was finding with PowerShell, which led me to eventually write this tool called Invoke Obfuscation. And so this portion down here is kind of what started me essentially coming to conferences, and open source has been a really important part for me personally as well as professionally. So in 2016, I wrote this tool called Invoke Obfuscation, and then in 2017, I wrote a similar tool called Invoke Cradlecrafter, and this was really fun for me to share tools with the community. But then very quickly, I saw attackers using my tools, like nation-state threat actors using my tools, and so that was cool, but also kind of frustrating to me because the scenarios were involving everyday citizens being targeted by governments. And so what I then did is I reached out and became good friends with this guy named Lee Holmes, who is at Microsoft. He is one of the original developers of the PowerShell language. And so in 2017, we did some joint research we presented at Black Hat USA and DEF CON called Revoke Obfuscation, which is using data science techniques to classify PowerShell commands and PowerShell scripts to detect them. However, I'm a creature of habit. I love doing more obfuscation. So in 2018, I was inspired by some financial threat actors and wrote a tool called Invoke DOSfuscation, which is obfuscation of command.exe and command line things of that nature. This year, I've released some other tools and co-released some other tools, one of which is related. It's called Maldaptive. It's LDAP obfuscation, and I'll be giving a keynote tomorrow morning here at KazHackStan on that research. But I just want to share this background because it's this kind of research and has really shaped the way that I, as a defender, write detections and do threat hunting. And those are some of the techniques that I want to share in this workshop to help all of us think maybe a little differently about how we detect malicious activity, obfuscation, and looking for signs of someone trying to be evasive. I spent 2 years at Microsoft, and now I'm at Permiso. But again, the main focus of this is going to be on a lot of the obfuscation techniques. Grassroot, this is an initiative I started 6 years ago in Kosovo and Albania for general security education, doing workshops, training, some of the training funded with the U.S. Embassy in Kosovo, and looking for opportunities to share this kind of information with high school and university students. So for this presentation in this workshop, we'll be looking at one specific attack technique. It's a very well-known attack technique for a lot of people, but we're going to go really deep into kind of an offensive, defensive back and forth. So we're going to write a detection, and then we're going to break that detection, and then fix it and break it, fix it, break it, and expose you to more and more of those kinds of techniques. So the technique is called Squibbly-Doo. It's a stupid name, and it's funny, and that's the whole reason the researcher gave it that name. First, what is it? And then I'll talk more about the history. So it actually has its own MITRE tactic or technique because it was so heavily used when it was first released. but it's a really specific usage of the binary regserve32.exe on the Windows operating system that allows remote, it's able to remotely retrieve a payload and execute the content inside of that payload. So that is what Squibbly-Do is. It was discovered by Casey Smith, a great researcher and a good friend of mine. And I remember the day that he tweeted this out. I came into the office drinking my morning coffee, and before I finished my coffee, we already saw people using this technique in the world. We were deploying network signatures, and we're already seeing people testing this technique very quickly. So rule number one is, if you share something on Twitter, then attackers are looking at Twitter and to see what to do. So before you try to detect something, you have to figure out, how does it work? What are all the components? And then where are our opportunities for detection? And this is very dependent upon your data. Do you have network logs? Do you have endpoint visibility? And so writing detections, you have to understand what opportunities exist from a data perspective. So how does this attack work? It has this specific command, and there is also a, actually, there's no way I can use my computer for this, is there? I think the formatting is getting kind of messed up for some of this.
You can change computer.
Is that okay if I do that?
Yes, okay.
Okay, bear with me for 1 second, because a lot of this is going to start to look really confusing if it's out of line. I do, yeah.
Do you mind if I stream this to a friend?
Huh?
Do you mind if I stream to a friend?
Yeah, that's fine. Well, wait, what are you?
Streaming to WhatsApp.
Oh, okay, yeah, that's fine. Yeah, go for it. HDMI? Do you have HDMI? Yeah, you can go straight in. Yeah, right here. Thank you. Yeah, okay. You're not picking it up. There we go.
This TV has some problem with my
Okay.
product.
Okay. Okay, I guess we can use this one. I think it's where the font exporting didn't go correctly. All right, sorry for the delay. I would say in the last year I've learned a lot about font exporting to make this a little seamless process, but so I apologize for some of the formatting might be a little off for some of the smaller details. But basically we have to understand how the attack works, what are all the components that are available, and then what data do we have to be able to write detections. So the attack is this basic command. First, what does this command look like? This is the actual tweet that he put out. He said, like, remote code in one tweet, and it was this command. So first of all, what is regserve32? The help file gives us some information. It's about a script component. It's about registering a script. That's what the regserve piece means. And specifically, he found that /u, we'll see later, is for unregistering it, but it still executes code inside of that scriptlet file. And the second part of the component is the actual scriptlet file. It is this XML file with several different pieces, but ultimately there's this JavaScript code right here which is running calc. And this is the POC that he posted, literally calling it program ID is POC, and this is what he posted on GitHub as part of this example. So those are the two pieces. This command has to be run on the system, and then the remote payload has to be accessible. So the execution steps involves first that command being run. So we have process execution, because I'm trying to understand what are the detection opportunities. Next is a GET request to that remotely hosted SCT file. So that's an outbound network connection. We then have the response, which is pulling that payload back. So an inbound network connection. And then we have the actual process now running this malicious payload in memory. So for each of these, we want to ask, what's the detection opportunity? Is it host, like endpoint, host-based? Is it network? And so for the first one, the process execution, we'd say, well, okay, that's running on the endpoint. So that's going to be a host-based opportunity for us to detect this activity. Next, it's a network connection. So do we have network visibility? Now here's where I'd propose, is there a way that if you only had host-based visibility that you could detect the network connection? And the answer is actually yes, even if you don't have something like an EDR, believe it or not. Inbound network connection, that's also going to be network, because then you can actually write content rules based on what the SCT file format looks like in the response, as long as it's coming over HTTP, or if you have, if you're decrypting HTTPS. But there's also the ability to detect on the host if there was a successful network connection specifically for this kind of payload. And then lastly, the running process is going to be a host-based detection opportunity. So what are some of the attack artifacts when this is run? We're not going to go into all of these details, but I like to think about this in three buckets. You have real time, which is what's happening right now. You have historical, to see, has this been run in the past? And then you have what I'm going to call future, which is this configured to run in the future? In doing a lot of incident response with Mandiant, there are many, many different threat actors that will set future access for themselves that may not execute that payload today, but it might be configured to run in 6 months. The way that we're going to approach resilient detections of this technique will allow you to find it in all three of these buckets: historical compromise, current, or even configured future compromise. So I want you to think about any kind of artifacts, whether it's like real-time visibility or forensic artifacts that point towards the future, into these three buckets here. So some of the most common ones that I recommend people start with is get visibility into process executions. If you don't know what processes are running on your system, you got to start there. For a Windows system, this is going to be your EID 4688. There is also Sysmon EID1, which is going to have very similar information. But the important thing we want to focus on is command line arguments, as well as you can update the 4688 to also include the parent process command line. These two things together in a single event log allow you to correlate two events without having to do any actual correlation in a SIM or any data source like that. Parent processes are really, really valuable from a hunting perspective. For example, I like to categorize executable names into these different buckets. So for example, a lot of attackers, if they want to run redserve32 or they want to run PowerShell.exe, how often do you see those be child processes of Microsoft Word or Outlook or web browsers? These can be indicative of exploitation, with the initial access being someone opening a malicious document. Or web servers. If you have a web shell that's uploaded to a system, how often should Tomcat or W3WP.exe be launching PowerShell, or 10 commands in a row, something like that? So this context of parent process is really valuable. Depending on the size of your environment, you can also take a block list or an allow list approach for hunting purposes to look for uncommon parent-child process relationships. So that's an incredibly effective way to start hunting in an environment, is to look for very uncommon parent-child processes, especially when you have a known definition for the parent process, or you have a known suspicion of a child process, or child processes that you only see on 2 systems out of all your last year's worth of telemetry, based on how far back you can look. Next, let's look at some of these forensic artifacts briefly. Prefetch, Shimcache, Amcache, SROM database, that's System Resource Utilization Manager. These appear on different versions of Windows, but it's another way that even if you don't have event logs, or if event logs have already rolled, they've already passed, and the evidence is gone, these forensic artifacts can contain information about process names, sometimes process paths. Even if they haven't been executed, sometimes just the presence of them being written to disk can still be found in some of these artifacts. It's not the purpose of this presentation, but if the concept of forensic artifacts is new, just know that you could spend 2 weeks doing dead box forensics on one system. I don't do that. Or you can take the value of these forensic artifacts and apply them to threat hunting. If you're a red teamer, you can use these artifacts to understand what kinds of things have occurred on the system or what kinds of things have occurred on another system, so you can start to target it. Many of these are located in registries. So if you can remotely access the registry keys of another system and say, hey, show me your prefetch, or show me your shim cache or aim cache, what all kinds of executables have been run on your system. So if I want to target a system that remotes into other systems, I can literally look in an environment, look at all the registry keys into shim cache and say, is mstsc.exe appearing in any one shim cache? If so, I know that you've run Microsoft or remote desktop, things like that. Persistence, I look for persistence for signs of historical execution as well as set for signs of future execution. One example of that would be if someone uses sc.exe to create a service. So sc stands for service create. If someone's creating a service in the future to run this command, then this command has not run yet, but it will run in the future. And so this is why I'm saying we're going to take a generic approach, not just looking for the process name is regserve32, but what if we find any of these values anywhere in the single string? That allows us to detect previous executions leading up to the actual known bad thing that we have in mind. Another interesting point here is that a lot of people really fixate on single ways of doing things, and this is very dangerous for defenders. So sc.exe is one of the more common ways of creating a service, but it's by no means the only way to create a service. So you can use PowerShell to create services, you can use the GUI to create services. So what I recommend people do is don't ignore this way of creating a service, but ultimately look at what are the artifacts that are created for a service so that you can detect it more generically. So for example, when you create a new service on a Windows system, it will create a 7045 EID in the system event log saying this service was installed. But there's a huge difference between creating a new service and modifying an existing service. And there are some notable APT groups that really fixate on modifying existing services because it does not create that 7045 event log. So defenders should not become over-reliant on that event log. So what should they focus on? Well, every service, no matter how you create it, is backed in registry. Registry is where that service definition is defined. So for both historical analysis as well as real-time analysis, if you can focus on this path, then you can see any service that's created no matter how it is created. So even if an attacker turns off your real-time telemetry and creates a service, you can go look in its registry and see what all services have been configured. And it'll be listed in this image path. So here's an example of me just using WMI to query, looking for any registry path that matches regserve32. Same using PowerShell get item. There's many different ways you can query registry, but these are a few of those options. Another really, really cool technique that we saw an attacker do once is using this failure command. So if you're creating a service, services are designed to run 2 or 3 times, and then if it doesn't work, it can have a fallback failure command. In the normal world, if your service is to start up a database, if it fails to start, you can say, all right, if that fails, then run this other script to go and try to fix stuff before you try again. Well, we saw an attacker create a service with a perfectly benign image path command. So it was just doing a simple command that was not malicious, but it was meant to fail after 1 minute. So 1 minute after failure, the service would say, all right, let's run the failure command, and that's where they had a malicious PowerShell command. So as defenders, when you're looking at these registry paths, don't just focus on image path. If you ever see failure command, it's very rarely used, but it's another way to get a service to execute your command. There are many ways to have persistent execution, but services are still one of the most common because they run as system. So it's a great way for an attacker to get system level execution. There's also some really weird things you can do with services with DLL loads that the service natively supports. So Casey Smith, the guy that came up with this, the whole technique in the first place, He spends all of his time looking through Microsoft documentation just to see what weird features do some of these binaries support that literally no one ever uses, because attackers love looking for uncommon things that are natively supported. So here's an example of just querying for anything that has the failure command defined. So as I said, new services, when they're created, they have that 7045 event log created. But if you're modifying an old system, then it's really important to focus on the registry paths, both image path and the failure command. So again, the purpose of this workshop isn't to teach you all these artifacts, but it's to show you there's a whole powerful, there's a lot of power in this knowledge, and learning some of these forensic artifacts as defenders or offenders is very, very important. Not necessary, but you can do things that other people can't, basically. And when these different persistent locations execute their payload, the parent processes are also quite different from one another. So as you're starting to do parent-child process relationships, understanding how often does run once or services or WMI PRVSC execute. So even if you don't have the ability to correlate activity between two different devices, if someone is moving laterally with WMI, this is always going to be the parent process. SVC host is running, it is going to call WMI PRVSE, then that will call the child process of whatever was invoked over that WMI process call create. All right, so that's the attack. All right, so Casey tweets this thing out. We then understand how does the attack work, and now what are our artifacts? What are the data sources we have to write detections for? So for the detection itself, we're going to start with, this is going to be rough. I again apologize about this. I will have to think through how to export these fonts so it shows up a little cleaner. But this was our original regsurf command. If we wanted to basically write a detection that anded all these things together, we could say, okay, let's look for regsurf32. Let's look for these arguments. Yeah, I didn't intend for this to be an obfuscation talk already. So let's focus on, well, these will disappear very quickly. So the basic idea is take the command and let's choose a couple substrings and say if all these substrings are present in an argument, then that's a detection for this technique. One thing as well is I typically never rely on the process name being something, because that name can always be changed, but also if you abstract it to only look at the arguments, then you can get a lot better coverage of the technique, as we'll see in an upcoming example, like that sc.exe example. SC is the process that ran. Regsurf didn't run yet, but if we were only looking for these substrings in the arguments, we would also detect that service creation command. So I'm going to change this from process names to be process arguments. So we're looking for these 4 substrings as process arguments in this example. And yeah, here's some examples of looking in process arguments would allow us to detect these scenarios, like a web server launching command that then launches regsurf32, or WMIC, the command line for WMI, remotely launching this regsurf32 command on a remote system. This would detect it on the source system as well, to say they're initiating a remote execution of this technique, or scheduled task creation, or not even looking at processes, just looking at the general registry to say, do we see these 4 combinations of substrings anywhere in registry? And here's us finding a malicious service that also contains that payload. So let's look at evasion techniques before we even look at obfuscation techniques. So we have our 4 strings. What can we change about this? As an offensive researcher, as an attacker, we always want to see what can we change. Because if we know that every defender in the world is using this simple 4-string technique, what are ways that we can break that? So the first one, does the process have to be named regsurf32? No. An attacker can simply rename that file to something else. We'll rename it to kc.exe in honor of Casey Smith. And now you can call Casey with the rest of the arguments, and it works. So looking for, this is called file masquerading, or file renaming. And so looking for this technique is important. So if you have visibility into the file information, like the file header, then you can write detections on the original name of the file, even if it's been renamed to something else. So I recommend focusing on file rename attacks as their own individual thing, but not bringing that into your detection logic for a specific technique. Next, we have this reference. That's right. File extensions also are not necessary. So you can just drop .exe and it still works. This is true of any executable And you can see we don't even have a full path to the register of 32. So if you ever look in your environment variables, you have the path variable, and then you have your file ext for file extension, and it basically goes through a traversal path of every single path in env and every single extension. That's how you can have search order hijacking of binaries based on if you're not defining the extension or the path. Let's keep going. That file extension is not necessary. So what about the file extension of this DLL? So we didn't talk about this a whole lot, but the scr_obj.dll, that's scr_object.dll, needs to be present for part of this attack, because that's required to know how to handle the SCT file. Well, it turns out you don't have to define that DLL either, so you can just remove that. So again, detections, if an attacker doesn't need it in the command, let's make sure we're removing it from our detection logic. So if we look at the binary name as well, can we just rename the DLL name? Turns out you can, so you can call it whatever you want. So now looking just for the exact string doesn't mean you're going to have a good detection. It does not mean you should not have detections for this. I think you should, but you should know that there is a way to evade that, so let's come up with deeper detections to detect those techniques. Because I would love to know the difference between a basic squibbly-do attack and a more advanced one. So let's remove that from our detections. So our detections are getting smaller and smaller. The file extension for the SCT file itself, turns out also doesn't matter. The file name, the file extension doesn't matter. As long as the content of that payload is still correct, then it will interpret it correctly. So let's remove that from the command, remove that from the detection. Now, come on. Let's look at these arguments here. S, N, U, I. My first question was, what do these mean? And are they required? So if we just look at the help file, we can start to get a better idea for what are these actually intended to do. So the /s is for silent, to not display any message boxes. Typically that's good. The attacker does not want to show up a box, but what if, let's say, you have an unattended desktop? Then you can run that command. I don't care if there's a box that pops up. I can just close that because no one saw it. So technically I don't need /s. So as an attacker, I could remove it. As a defender, I think I'm also going to remove that from being required. And again, I'm doing many levels of detections. So having detections at each layer is quite beneficial, actually. Next, we can look at /n. Just basically not calling these two function calls must be used with /i. Turns out also totally not required. The payload still works without that. So let's remove it from the command and remove it from the detection. Keep going. Fun card trick. It's fun to have some breaks in between obfuscation. I wish that was me. I don't have that skill set. So cool. All right, let's keep going. So that wasn't even obfuscation. That was just evasion. What are the things that are required? What are the things that we can remove? And let's make sure our detection is taking that into account. So now that we've removed a lot of the things that aren't required, what are actual true obfuscation tricks that we can use? So this is our current detection. We're going to break this into two pieces. Again, I apologize for this. It's basically /u and then this /i and the URL is what we're left with. So first, HTTP. Is this required? Well, no, you could host it on HTTPS. You can also host it on FTP. You can also reference a UNC file path, local file path, etc. At this point, I kind of separate local execution with remote execution and treat those as now two separate branches. So again, we start with one detection and are branching out to 5, 10, 15 different detections. So we could convert this to a regex, a regular expression looking for HTTP, HTTPS, and FTP. We'll stick with that for now. These slashes, so we have /u and we have /i. There are two obfuscation techniques that if you don't remember anything else from this entire workshop, I want you to remember these two techniques. The first one, anytime you see a slash for a flag or an argument, try using a dash. Windows, this is different per binary, but most Windows binaries will accept a dash or a slash with no issue. If you really want to be crazy, there are many different dashes. There are like 6 or 7 different dashes. There's Unicode dashes. There's a dash and a hyphen are technically different. There's a long hyphen, short hyphen. There's even some dashes that are vertical. I think it's like a German dash or something like that. This is where it's very important to understand what normalization might occur. So if you're using like Windows 10 and you paste in a Unicode dash, it's going to keep that dash in the event logs. If you use an older version or you're using it in PowerShell, sometimes the host application will convert it before it actually logs it. But there are still possibilities where that Unicode character can be the one that's logged. So as defenders, you could either write crazy regex that's taking into account all the dashes, or you could do normalization before you apply the detection, or you could simply look for the presence of some of these Unicode dashes. That alone might be enough of an indicator for you to say, I'm interested in why this person was trying to use this weird dash. This is what I call looking for indicators of obfuscation, which to me is telling me someone is likely trying to hide something. What is it? And why are they trying to do that? So in this case, we're going to do a simple regex saying I'm looking for the dash or the forward slash. What about the forward slashes in a URL? Do those have to be forward slashes? Again, it depends on the application, but in this case, we can actually use backward slashes. PowerShell even lets you do forward, backward, backward, forward. They don't even have to be the same. So again, I would encourage you whenever you're looking at these kinds of scenarios, just try, just forward slash, backward slash, allow you to change them. And if so, make sure our detection can handle that difference. /u and Smith1, the order can be reversed here. Why does that matter? Well, it matters because in our detection, we were assuming that there will be a white space after that /u, but if we push it to the end of the command, there's now no white space. So we should make sure that we remove that. And again, this is a crazy regex to try to handle some different scenarios. Let me keep going here. So also, do we need to have a space after the /u? The answer is no. It turns out, this was a crazy accident. When I was testing this, right before I hit enter, when I moved the /u to the end, I accidentally hit 0. Don't ask me how. But I accidentally hit 0 and the command still worked, which made no sense at all because what does U0 mean? And so I was like, okay, well, /u or -u means uninstall. Are there different levels of uninstalling? Like, why would it support these numbers? And so I tested it, 0 through 9 all worked. And then I said, this feels too, like there's no concept of 9 levels or 10 levels of uninstall. What if I tried another letter? So it turns out A through Z also works. Turns out literally anything you want after U works. Now, why is this? Again, this is dependent on the binary, and Windows often does this, but basically, if you have a binary that has multiple, well, it doesn't even need multiple. When a binary has multiple arguments that start with the same substring, it will allow you to define substrings of that flag as long as it uniquely resolves to that one thing. So since there's no other argument that starts with /u, if it sees /u, it disregards anything else after that up to the next white space. So that's why we can literally make /u be this, and it's only going to interpret the u and then drop everything else after that. It is logged exactly like this with all those garbage characters, but it'll keep that in the logs. So this means that we can't even rely on there being white space or the end of the command. We just have to know that /u can be followed by anything else and still work. Again, this one is slightly dependent on which binary it is, but it's a pretty cool technique for evading. So how reliable is the white space before these arguments? Like, yes, we can add garbage characters after an argument. So this is the second technique. Again, if you only remember 2 things from this whole talk, the second one is this. The first one was slashes and dashes, trying that interchange. The second one is, and this is a very Windows-specific thing, is this right here, which is the double quote. So if you have double quotes, you can put them just like that and now essentially erase that white space that was present. You can put many different pairs of double quotes, and it turns out it doesn't even matter which argument it's around. The whole point is throughout the entire command, as long as you have an even number of double quotes, then the command will still work. It has to do with basically how when you have nested commands, you have to basically stack quotes or escape things, but what's really nice is that quotes don't need any escaping. So even if this command had like 10 commands buried inside of it, those double quotes are going to persist inside of every command. Now, the really crazy part, first of all this shows up this way in the event logs. And whether it's a system event log, security event log, an EDR solution, like they all get that data from the same ETW stream, which is event tracing for Windows. So these quotes are going to show up and you have to take them into account when you're writing detections. The great thing is there are some binaries, like let's say that redserve32 didn't support double quotes like this. Well, if I launch redserve32 from command.exe, command.exe does support these double quotes. So I can load up redserve32 with double quotes inside of command.exe, and when redserve runs, those quotes will still be present. Even though if I copied and pasted that command, it wouldn't work. So this is where it becomes a really weird stacking technique for attackers, that if you can start with a binary that receives all those values, then you can kind of like dirty up all the child processes in ways that they wouldn't normally allow. So double quotes are terrible for defenders. And I've still not seen attackers use this as much as they really could. But you can also chop up, it doesn't just have to be for white space. You can literally break up any single string that you want to. So pretty much any of our detections we had, we can completely destroy with double quotes like this, right? Seeing a couple smiles. Yeah, this is crazy. So like, bad news for defenders, great news for attackers, but it can be good news for defenders if we're aware of the technique and ways of mitigating it. There are a couple different options here. We could do, I don't recommend the first one, which is come up with crazy regexes to handle any possible character combinations. One of the best things is if you have the ability in your pipeline to do some kind of data normalization, that's usually the most effective way. And you can be smart about it by saying, how many of my processes even have, let's say, more than 2 or 3 pairs of double quotes? Again, if I'm looking for signs of obfuscation, there are very few enterprise products that load up commands with double quotes. And so how many of your process executions in your company or your clients have this many double quotes? And then from there, you can go and do the normalization and see what else exists. And this is just some simple like PowerShell commands just to do that kind of replacement logic as well. One other thing I like to do is, in this case, we're looking for very specific strings for a very specific attack, right? We've spent a lot of time on one technique. That's why I really encourage you to write detections and filtering for signs of obfuscation, for signs of things that look different. A very generic approach to that could be, what if you were to do a comparison of before and after, even like non-word characters? So let's remove all special characters. What percentage of my command was special characters, right? Like if the normal command was 100 characters and now it's 180 because I have 80 special characters in there, then why is that the case? Before and after analysis of using like, there's some data science tricks called like a bag of words. How many words greater than 5 length showed up after normalization that were not there before? That tells me that special characters were used to chop up larger words into smaller ones. And that's a nice feature for me to use to see if an attacker was explicitly trying to evade based on that. So that was specifically looking at detection opportunities for the arguments itself. So now let's look at some non-argument stuff. This is getting a little back into some of the forensic artifacts, but some of these capabilities you can use for real time. So for DLLs, so dynamic link libraries, basically when redserve runs with that payload, remember it grabs the SCT payload, it downloads it, it then runs it. Now redserve32 is going to execute anything inside of that JavaScript. Well, depending on the payload inside of that JavaScript, even if you don't have visibility into that payload, you can see what DLLs are loaded, and that starts to tell you something about what kind of functionality that payload is capable of performing. So like, for example, we'll look at a couple examples later, but here's some additional non-argument things that you can look for. What are child processes of redserve32, regardless of what its own arguments look like? Because again, like people immediately started to use this technique to run, what was it? There's a researcher named James Forshaw that came up with .NET for J. What was it? .NET to JScript. I'm blanking on the name. It's basically using JavaScript to be able to load assembly. And he came out with that shortly after Squibbly-Do, and people merged those things together, and it became a killer combination. Because now people can run any unmanaged binary directly from JavaScript, loaded by redserve32. When you do that, there are very unique DLLs native to Windows that are loaded by redserve32 to facilitate that. So, for example, jscript.dll, jscript9.dll. Those are loaded by any process that is doing JavaScript. How often does redserve32 load JavaScript in your environment? If you have sysmon logs, this is EID7 to say image loads, DLL loads. And it's a really powerful hunt to even see what all processes are loading JavaScript in my environment. Now, we don't know what the JavaScript is just by that, but that DLL load tells us a lot of information. Historically speaking, if you remember back on some earlier slides, we talked about prefetch files. So C Windows prefetch is the directory for prefetch files. Prefetch files exist to prefetch files. So whenever you run an executable, Windows records the first 10 seconds of every DLL that's loaded, and it records that in that prefetch file. The whole point is next time you reboot your computer, it goes through all of your most recently used executions, and it locates on disk all those DLLs to make sure they're still present, so that when you want to run that again, it assumes you're going to want to rerun this because it's a frequently run binary. It knows exactly where those DLLs are. So it's a usability feature. Well, as defenders, or even as red teamers, we can go and parse prefetch files and say, hey, you know what's weird is that 2 weeks ago, you had a prefetch file entry created for regserif32, and I can tell you in the first 10 seconds that it was executed, here are the 17 DLLs that it loaded, and by the way, jscript.dll was one of them. So again, it's not the whole truth, but it's a very interesting indicator to say if JavaScript running in regserif32 is uncommon, this historical artifact can exist for months or even years later and tell you when that thing happened. Yeah, forensics is really freaking cool. These are some additional image loads that are interesting. So there's our JScript and JScript9.dll. wsham.ocx is another one for script host runtime. VBScript, system management automation. This is actually PowerShell. That's the DLL that is PowerShell. So if people are doing unmanaged PowerShell, that's another great DLL to look for as well. And you can also go through and start to baseline what images are loaded, what DLLs are loaded by some of these binaries, and start to look for uncommon image loads. Just like we look for uncommon parent-child process relationships, look for uncommon process image load or DLL load relationships. So we've spent a lot of time looking at some forensic artifacts, looking at different approaches to command line arguments, looking at those forensic artifacts for historical detection purposes and future-based detection purposes. But how do we actually use this? So for all the command line argument stuff or the forensic artifacts, you need some kind of either EDR or SIM or using local tooling like WMI or OS Query to retrieve that information from all of your systems. So it really depends on what artifacts you're trying to target. I'm going to go for just a couple here. My basic approach here, as I mentioned before, is use many different layers of detections. There's no one catch-all. Write the detection for the generic, run-of-the-mill tweet, like the exact proof of concept. But then go through and write, okay, what if I was writing one with minimal arguments without obfuscation? Now let me do one with obfuscation. Let me look for general obfuscation being present in any binary. I kind of write these out. I kind of mind map all the detections. So it's just proof that one example of a very easy to detect technique, if you take it far enough, it can lead you to find many undiscovered things completely unrelated to this. But now that you have some of these ideas in your mind of slashes and dashes, double quotes, rearranging things, hopefully it'll give you some more ideas for writing detections. Because there are some attackers that will use just one or two subtle techniques like this, and it does not look obfuscated at all, but it's minimally obfuscated to evade detections that don't take this into account. Any questions about that, about the process arguments or any of those artifacts that we looked at? All right, yeah.
Does normalization broke the payload if you remove the quotes? Like, when do you deobfuscate in the process of preparing the defense?
Yeah.
Can you remove them and then run it? Or it will broke because there is no spaces?
Yeah, no, great question. So the question was, yeah, if you do some normalization like removing quotes, then will it actually break the command? So it's a good question. So for me, normalization, I'm never doing normalization between the thing actually running. Like typically the thing is already run. When I'm investigating the records, the event logs, then I can do normalization and compare the before and after, but I'm not actually executing the thing that ran. But it's a good point, especially in scenarios where, yeah, I'm removing all special characters. Well, some special characters are required, But if I remove all of them, it's just to do some statistical analysis to see what percentage of this was special characters, or to try to remove some of those obfuscation techniques. But not for the purposes of running it, just for analysis. Because it can simplify, now I might not have to write some crazy regex handling a lot of quotes. I can remove all the quotes and then just focus on what's left. There are some obfuscation techniques that will rearrange characters and reassemble them in memory. And for those, even removing special characters doesn't help you. But there aren't explicit things like that I've discovered well, that's mostly true. Yeah, for the most part, that's not a challenge that we have to deal with on the command.exe. It is something you have to do in scripting languages. Great question. Any other questions? Yeah.
How can organization protect themselves from attack that utilize reg service 32.exe for command that obfuscations?
Yeah.
How can organization protect themselves?
So how can
what security measures should they take, or what security should they do?
Yeah. So what measures can an organization take to defend themselves against an attack like this, obfuscated or not, right?
Yes.
Yeah. So it really depends on what tooling you have available. So detecting it is the first step. But for example, if you have the ability to look for, does Redshift32 ever make network connections at all in my environment? Should it? Like, there are legitimate cases where it should, but if it's not common in your environment, then can you block based on that? Does Redshift32 need to be used at all for a lot of systems? If you have that level of granularity, you could start to implement application block listing. Make sure that your baselining is thorough, so if you're not blocking something you actually need, but that is something you could do. I'm not familiar with many solutions that allow you to block which DLLs can be loaded by which executable, but that could be something to look into. But yeah, I think most people probably aren't at the prevention level, they're probably just at the detection level. And so everything we talked about should be applicable based on what logs you have available, or what capabilities you have to look at some of those forensic artifacts. Yeah, good question. Yeah.
Sorry, to clarify, so the threat intelligence, with the context of your organization, can detect at least problem.
So the question was, can the company I work for detect this based on our?
Can a company that have threat intelligence
Okay.
running in their environment, that the threat intelligence is aware what it's using?
Yeah.
So can it detect it with rules of confrontation from the threat intelligence?
Yeah. So can a company with threat intelligence detect this? I mean, the threat intelligence. It could. Scenarios in which that would work well is if there's an attacker using the same exact command, like a very broad attack. Like in that case, yeah, as long as you're not the first couple hundred victims, or if you're in the second, if you're after the first 5 minutes, then yeah, maybe like Microsoft Defender can go through and say, hey, we're going to push a custom rule saying this command with this IP is malicious. But if you're a targeted attack, that's not going to help you. So. Threat intel can be valuable. I think good threat intel is valuable. I think a lot of it is not valuable. But that's why, again, as defenders, looking at the technique itself, I feel like is very valuable in the absence of threat, any kind of threat intel. But yeah, good question. Yeah.
I want to ask about how many layers of detection is overdoing or optimal for the organization. Like, there's always some blood, and if we overdo it, there is problems with optimization and something like that.
Yeah. How far is too far? Yeah.
Of course, the big higher amount is better, but it takes more resources. And what is optimal in general?
Yeah, no, your point about resources is correct. Yeah. So when do you stop? When have you done enough layers of detections? When is too much? I would argue what I showed you is probably too much for huge organizations. My experience has been writing detections for Mandiant, FireEye, Microsoft, where we're writing for thousands of customers, and we can't tell them stop running this thing or this is sloppy. Like, we have no say in that. We just have to make a rule work for a huge percentage of the world's devices. So for them, resources is very important. So we could not do all the crazy stuff I was talking about because it's just too resource intensive. We have to think of more creative ways. That's why I'm saying generic approaches like looking for presence of too many special characters is a good first step. If we can take 1 billion process executions and reduce it to 40,000 with one step, now 40,000 is a very small number in comparison that we can do a lot more analysis on. So for those kinds of techniques, I prefer to stay more generic and not try to do it for every single MITRE tactic or binary. But that's where the value of frequency analysis comes into play. If you can extract features from a command and then start to group and stack and say what are the most uncommon combinations of features for regserve32 or for any command that has HTTP in the arguments, like think like more weird and generic like that, then you can start to look for what are the most uncommon binaries that led to that. Now if an attacker ran kc.exe and did that command, that's the only example in the world of a binary called kc.exe that has HTTP in the arguments. Like that stands out even if you're looking at billions of events. I wouldn't implement everything exactly as I showed here for a huge organization unless you have the resources to burn. Otherwise, try to think slightly more generically. But it's a personal struggle because I want to be able to say I've thought through every way I can conceive of to detect this, but it's not going to be realistic for a lot of people depending on their tool sets or resources. So yeah, good, excellent question. I mean, it's always a balance, and too much security can bring everything to its knees if it's using all the resources or slowing things down. So that's always a balance we have to play. But yeah, great question.
So
yeah.
Does normalization is used when you detect or when you only making indicators?
Yeah, so normalization, I would say for both, depending on how you, I mean, for me, indicators are detections. That's just how we defined it at Mandiant. So like,
so you first normalization, then make implementations, indicators, and then push to the agent. And it looks like, well, the agent does not normalize.
Typically, no. Sometimes the operating system, like Linux operating system, normalizes all this stuff, like just by its very nature. But since Windows doesn't, then yeah. But like I think about like a funnel. Like again, if your input is like 1 billion commands, if you have the ability to define multiple pipelines, I would define a separate pipeline to say take all 1 billion commands, any of them that have more than 6 double quotes, take those, and now you're going to go through the normalization pipeline, the quote normalization pipeline. Because I might have 17 detections that want to use that normalized pipeline. So let's do the normalization once for that down selected 40,000 commands, and then pass all those commands through those detections. It can get very complicated, and so again, it depends on your tool set and the size of the data. Because if you have a smaller environment, you don't need to do all those pipelines. You can just probably run 17 rules, and each of them does the same normalization, and you might be perfectly fine. It all depends. When you start to hit performance issues and scale, you have to start to step back and think of a more performant way to do it. And that might cause you to say, it's not worth running some of these detections. We need to detect this another way. Yeah. But one last thing about this scenario is think of different ways to reduce data into smaller buckets or filters. Again, one of the things I mentioned was, what if you have 1 billion events, what if you reduce it first and say, show me all events that contain HTTP, right? Or that contain more than 6 quotes. What if we don't have to stay confined just to the process arguments? Can we say, show us all command line arguments that have made a network connection? Like, now that's a lot smaller number of processes than the 40,000 even. And so when I'm talking about adding labels, those are the kinds of things that I'm thinking of. How often do you see a process making a network connection and the arguments of that process don't contain HTTP? That does happen fairly commonly for native Windows binaries, but you can start to remove those things. A lot of attackers will inject into common binaries in System32 and Sysfile64. So how can you start to look for those binaries making network connections over uncommon ports? Now we start to stack process name and path with port number. And so if you start to see 389 or 3389 or 445, like, hey, is this an attacker doing SMB scanning from services.exe? Like, that shouldn't be the case. So frequency analysis can really help you hone in and find, hey, if I'm doing 10 or 15 different frequency analysis searches and then grouping the results, this one process hit on 3 different frequency analysis, like uncommon things. Like it's in the bottom 1%. And that can help lead you to many different ways in which a process can be acting weirdly. So yeah, again, it all depends on the tooling you have at your disposal. But these are really fun ways to catch attackers that are doing really clever things, but ultimately they're still generating telemetry. So they might have evaded rules looking for command line arguments or rules looking for anti-malware scan interface, the AMSI. but they're still going to be making network connections. Information is leaving that device. How can you correlate all those things together? Awesome, great questions. Let's go to the second part of the presentation, which is now looking at the actual payload itself, and let's apply some of these same concepts to the actual scriptlet payload. So this is the default payload that Casey posted on GitHub. Again, the actual malicious command is written in JavaScript here just to run calc.exe, but it can be any malicious JavaScript that you want to put in there. So the first thing that I do when I look at things like this is what's common, like what's there by default. Most people are copying and pasting this POC and just changing the actual command. So let's highlight all this stuff in green and start to look at some of these things. First of all, in this class ID, it is a lot of zero, like mainly zeros, and then it ends with feed ACDC. Casey Smith loves ACDC, and so he literally thought this would be hilarious to say feed ACDC. Most people don't know this, and they just use that. They think this class ID is actually important. So, as I said with arguments, let's write many layers of detection. So I'm certainly going to write a detection looking for this exact class ID because there are a lot of people who'd never change it. So this is a dead giveaway that someone used this POC. How can we detect this when it's being in the response when it's being called? Well, you can write network detections using something like suricata or snort rules. There's lots of nuance here, but this basically allows you to write detections based on the content, the behavior of the network packets, and grouped into sessions if you want to. Part of my intention for talking about some of these specific detection technologies in this workshop is to introduce people to how simple you can start with these. Because if you Google examples of snort rules and other detections, just like if you Google examples of regexes, then you'll quit before you start because they're like a mile long and insanely complicated. So I want to encourage all of you, you can start very simple with things like snort rules, and we'll look at a couple examples of these. So this is an example of a snort rule specifically looking for this class ID. The snort rule itself is basically saying generate an alert for the rule. What kind of traffic are we looking for? We're looking for TCP traffic. Actually, Snort in the last year updated to a new version where you can actually write this portion a little differently. But basically, you can write them based on like source IP import and then destination IP import. For me, I actually don't care about which ports or which IPs. I'm looking just at the content of the payload itself, which is this here. And there's a lot of really cool things you can do for performance purposes to make that more performant to look for that payload actually within the rule. Another thing we can do is look for that comment that he put in there. Proof of concept, Casey Smith. This is his Twitter handle. Again, a lot of people don't remove any of these comments and they just run the payload with their custom final payload. So if attackers are going to be lazy, I'm going to benefit from that and catch a lazy attacker. Because I want to know if it's a lazy attacker. I still want to catch the good ones, but the lazy ones I want to be able to easily label as someone that just copied and pasted. I'm going to skip some of the pros and cons for network signatures, but there are considerations to take into account. But even internal network traffic is a great way of detecting lateral movement, whereas SCT files can be the function in which they do that. So other things that we can look at here. The program ID, he listed as POC. So immediately, let's write a rule for looking program ID as POC. But then, if you have the ability to access lots of legitimate scriptlet files, what does program ID normally look like? This is where I like to stop and start to build a library or a corpus of examples and look for what is common, and then look for the negation of that. So what I found is that POC is Casey Smith's example, but you also start to find things like program ID equals bandit, or is short JS rat, which is part of JavaScript rat. MSF, Metasploit Framework, Win32 Com Debug, part of the Empire framework. So you can start to look for open source offensive tooling and look at what templates do they use, and then how can we write detections for lazy hackers using any of those templates. And now we can also look for what are program IDs that don't match this. So an uncommon program ID can potentially be another way for you to write detections based on this information that you've gathered using open source intelligence. And so we can write a program, snort rule looking for prog ID that does not match, or that matches these specific examples of program IDs. The next thing I ask after we look at what's there by default is what is actually required. Just like with redsurf32 and the arguments, what things can we remove and it still functions the same? So everything that we have in yellow the version number, prog ID, comments, even this C data, we can just completely remove every bit of that, and this is still going to work as expected. So as defenders, never put too much weight on something that can just be removed out from underneath you. And you don't really know this until you try piece by piece removing things to see if the payload still works. And that's exactly what I did here when writing these rules. Next, what can change? So again, just like with the arguments, we remove the things we don't need, but what are things we can actually change? They are still required, but we can make it look different. First thing is all these double quotes can be single quotes. And again, this is now, we're getting into XML level stuff. And so this is beyond, like scriptlet is a subset of XML. So any kind of XML tricks you can think of, can you apply those here? Yep. So the class ID, as long as it's a valid class ID, you can change that, and you should change that. Scriptlet, this is a really interesting one because when my team and I were writing these snort rules, the day that Casey released this, we were writing our anchors to be these scriptlet tags. And we were trying to find, is there any way that we can make this work without the scriptlet tags? And my manager actually put out a challenge on Twitter saying, hey, I'll pay people some money if you can come up with a way to make a scriptlet file work without this. And a researcher at SpecterOps named Matt Nelson came up with a way, and that is the component tag. So he's a guy that has written all these cool tools in JavaScript, and so he's like, oh yeah, duh, like scriptlet is just one. You could totally use component and it would work just the same. So scriptlet and component are the two main ones that I've seen people reference as anchors. But again, sometimes going and talking to someone Matt Nelson is a security guy, but don't discount the knowledge that non-security people have in a domain you're not familiar with. So go talk to a JavaScript front-end person and see, hey, what weird tricks can you do with JavaScript to execute a process? And you can learn a lot from people that aren't working in security because they have cool tricks. Next, script language equals JScript. There are many different languages you can define in here, because again, this is the actual payload that's being run. Turns out that you can write the language to be JScript, VBScript. Also, if you've never looked for JScript.encode or VBScript.encode, it is fantastic. Fantastic for attackers and really interesting for defenders. So I would encourage you, look for references inside of payloads for that JScript.encode or VBScript.encode, and the actual payload that comes out, if something is encoded in that way, is going to look like this. And importantly, these green substrings, it's the same substring or similar substring kind of in reverse order. These will always be the 4-character header and 4-character tail of any JScript encoded or VBScript encoded payload. So when we actually discovered this, we took the generic approach to say, let's look for anything that contains these two substrings anywhere. Event logs, registry, and you know what happened? We found an attacker that was storing their payload as a VBScript encoded string inside of a random registry key. And we found that because we went through this process and wrote a very generic detection looking for those things. So again, it doesn't mean it's malicious, but it means someone encoded this for some reason. Are they trying to hide something suspicious, or is this just some legitimate usage of VBScript encode? But yeah, that was a new concept for me when I first saw this technique, so I thought I'd share that with y'all. Additionally, you don't even need to define any of that. You can just remove the language entirely, and it's going to assume that JScript is the default. So even writing a detection looking for all of these is not actually going to be a great detection, because you can just skip defining the language and it's going to assume it's JScript. Next, at an XML level, we can add white space in lots of places in XML documents. And then if we go down to the actual main payload, we're now looking at JScript. So what are all the different obfuscation techniques we can do there? We can add a white space. I mean, this is a whole different research topic of language-specific obfuscation. So I'm going to skip that for now, but just know that there's a lot of craziness that you can do inside of there. And then you can also remove all the new lines. Like this could be your entire payload. So again, keep this in mind when you're writing detections. Don't assume that something has to be within 1,000 characters. It could be 10,000 characters. What are size requirements? There's a lot of different factors, so I would encourage you to test in your own environment and look at the data that's produced as you're writing these kinds of detections. So we can write snort rules for these detections. I'm going to skip just a couple ahead. Yeah, so you remember at the very beginning when I was outlining the attack and I said for the network request and the response, there are ways that you can use host-based artifacts to actually detect network activity. And now I want to show you what some of those are. I'll talk briefly about the outbound network connection. There are, depending on how the network connection is made, there are some registry keys, especially when you're using PowerShell download cradles. There's one called RASMan, it's Remote Access Server Manager. And there's another one that starts with RAS, I forget, but it'll actually create a registry key referencing PowerShell the first time you use a PowerShell.net download cradle. And so you can actually see when a download occurred even outside of having any network logs or even Windows event logs. But in this case, when you actually download that scriptlet payload, people call this attack a fileless malware attack. It's a kind of trendy term. I've seen very few examples of truly fileless malware attacks. Now, it's fileless in the sense that you're not explicitly telling it, download this file and then point to it on disk and run, but it does actually get written to disk in an indirect way. So when you do this attack, whether you're using Regserve32 or MSHTA, a lot of these kinds of living off the land binaries, a copy of that remote file is going to end up in your iNet cache or temporary internet files in local app data. Now, why is this important? Well, if you're an attacker, you should probably go clean up that file. Otherwise, your entire payload is sitting on disk for defenders to discover. For defenders, you should be looking in these locations, looking for the presence of any scriptlet files or any of these known bad substrings we've been looking for. And so for this, all the things we looked at for writing snort rules for network detections, let's take those same concepts and write them in Yara rules. And Yara is one of the coolest detection rule platforms ever, written by a really cool guy, Victor Alvarez. And so anyways, I want to again show you some really basic examples of writing simple Yara rules in the hopes that you'll be encouraged and excited to go write some of your own. Because you can start with very simple Yara rules, or you can write truly crazy Yara rules that make my head hurt just by looking at them. So let's start with the simple ones. In the snort example, we were looking for the default POC SID. Remember that crazy feed ACDC. So this is what a snort rule looks like. If we wanted to write a Yara rule, we'd start by just saying rule and then the rule name. And then we're going to have a couple sections. The only required ones are strings and condition. And so strings, we're going to define a string name and then the actual literal string. And then the condition is just $sign to reference that variable. This is now a functioning Yara rule looking for that one string. Very basic. And Yara, it runs on any OS, and you can essentially run the Yara binary, point it to any number of files, and then it will run all those rules against any number of files that you have. So you can run Yara rules against an entire operating system, against any file, and now detect if there were any files that contained this exact string, regardless of the kind of file, what it was named, etc. So here's another example of using the looking for one of the default comments in a Yara rule. Now, what's really, really powerful about Yara compared to network detections is you have the ability to do extremely robust and/or logic. There's many other things Yara can do way better than a network rule because of just how and when it runs and performance implications. But what this means is instead of writing two completely separate rules for these two default things, we could actually take both of those strings and merge them into a single rule like this, and the condition now says the CLS ID or the comment. And so we can start to get really creative. And you can even do things like have 20 strings and say any 4 of these, right? Like that's a really powerful capability to be able to do. You can also have Yara rules reference other Yara rules. And so one of my previous coworkers, his name is Steve Miller. He has a crazy cool blog post when he worked at a company called Stairwell. He has a really different way of looking at detections for Yara rules that I've really learned a lot from him. And he uses Yara as label mechanisms. Add many different labels and then combine labels. And I think that's the best way to find really advanced nation state malware that has been discovered no other way, is by applying a lot of these features and labels in really creative ways. Not the purpose of this talk, but just know that you could do a lifetime of Yara rules in really creative ways, especially if you have access to things like VirusTotal or large file repositories. Here's some other examples of having regexes. and then let's say 2 different sets of program IDs, and you can say any of those. There's just a lot of really cool, powerful things that you can do. And in my opinion, YARA rules are a lot more readable than snort rules when you start to get into some more advanced things. This is not a great rule. Like there are many better ways to write this rule, but I at least want to show you the power of the and or combinations. And just like the command line arguments, my advice is write many different layers of rules so that you have the default rules and then the deeper rules and then rules that are just looking for signs of obfuscation. And again, every rule, don't think of a rule hit as an alert, think of it as a label. Does any one file generate 7 different labels? If so, depending on the labels, that might be the most interesting file on the system. Let's go and analyze it further. Let's look at the timestamps, see when it was created, what other files were created around the same time, move more into forensic investigative analysis mode once you've found a file of interest. Because of a lot of the crazy obfuscation stuff I've done, I write a lot of crazy YARA rules and snort rules that have gotten me in trouble before. And so I had all these rules running in VirusTotal, which is part of Google, and it allows companies to create YARA rules, upload them, and it will run YARA rules against every file that anyone uploads to VirusTotal. So I got this email one day from somebody at VirusTotal saying, hey, one of your rules is slowing down our scanning system, as in the whole world scanners, like none of their stuff is working because of your one rule. And he said, I think it's because of this crazy regex. And he basically said, I've disabled it, but let me know if you want me to help optimize it. I'd be curious what you're trying to do here. And so it's a very polite email, and I was thinking, like, I wonder who this guy is. So I looked him up. His name is Victor Alvarez. He's the guy that invented YARA. And he is at VirusTotal. His company is VirusTotal. And so this actually happened 2 or 3 times where he'd email me about a rule and I would fix it. But I emailed him and said, hey, are you okay if I take a screenshot of this message and share it? Because I've never met anyone as free and open with your time as you. Like, you could have just said, hey, stop writing stupid rules, you idiot. But super cool guy. I've never met him in person, but yeah, it's really nice to see people who are super brilliant and still helping people and not making them feel stupid. So if I could give some life advice, always help each other out. Never make people feel stupid. You'll never be the smartest person in the room. That's a good thing. People don't have to know how smart you are. If you're humble and help people, it makes life go a lot better and it makes life a lot more fun. So anyways, that's the end of the philosophical topic there. But yeah, that's pretty much the end of this workshop for the technical details. So just a quick review there. Whenever you have a known thing, in this case, that tweet was a new known thing. Here's a technique. What do you do with that? First, understand how it works. Let's outline the attack. Can we gather samples to start to build a corpus of benign SCT files or malicious ones to start to look for differences in how people have modified them? Let's look at the detection opportunities based on our data and based on our tools. Again, if we have no network data, there's no point in writing snort rules, right? If we have network data but can't deploy snort rules, maybe we shouldn't invest that much time in snort rules. Let's focus on endpoint data or forensic data or event logs, whatever we have at our disposal. Develop multiple layers of detection. Defense in depth is true for detections as well. And this will also help you, again, if you think about detections as labels and not alerts, then if you have something that is really crazy, like crazy obfuscated, you should have 2, 3, 4 labels that hit on that one example. That's going to tell you a lot of information. And think about labels. If you can query all of your labels and group on which processes generated more than 2 labels. What if you have labels that are defined as obfuscation labels versus known bad labels versus uncommon labels? Like, think about it that way. It takes more time to start, but it will allow you to look at vastly larger quantities of data and find interesting things far more quickly than people that are looking just for specific known bad. And also, don't forget the behavior-based detections. Don't just think about what is the command line argument, what is the payload structure. Look at all the behavior. Like I think as our industry, we spend too much time fixating on initial access. Like, how did someone initially run this command? Well, every attacker, no matter, let's assume that they're going to get initial access and we missed it. What do they do next? Like, if they're injecting into known Windows binaries or known Linux binaries, Let's start to baseline what those binaries are doing. Would we expect an attacker to be doing SMB enumeration? Cool. Then what processes issue more than 100 connections over port 445 within a minute? If you have a SIM that can do that kind of correlation, run it. Go check it out. See what binaries are there. And if you're a red teamer, you should do the same thing, because if there are binaries that do that, then whenever you want to do SMB enumeration, inject into that binary, because now you're fitting in the exact MO, the modus operandi of that binary. So that knowledge is really powerful whether you're on defense or offense. Baselining approach, I don't use the word baselining lightly because it is a very easy thing to say and a very difficult thing to do effectively. But if you can, try to figure out what normal looks like in your environment, and then you can write specific rules based on the inverse of what is normal. And on that note, you can do things like say, okay, let's write a rule that's just labeling SCT files, the most basic way. Let's start to make some assumptions and then break them. Does an SCT file need to start with an XML tag? No. And there are actually examples of scriptlet files that start with GIF 89A. Why would someone do that? Well, the scriptlet file, like many languages, can traverse and find a nested payload that is a correct scriptlet file. But a lot of engines, like VirusTotal, says, hey, this is a GIF file, because it's looking at headers. Again, for red teamers, spend time understanding the tools that defenders use, because we have to make performance trade-offs all the time, just like you were talking about with the resources. A performance trade-off is we can't run every rule against every file. So engines like this will look at file headers, or they're called magic headers, and see what kind of file is this, and then determine which subset of rules to run against that file. So attackers doing this, almost no rules are written for GIF files, and so it might actually skip running the rules that would have detected this otherwise very easy to detect payload. And again, as a defender, you can detect this by saying what's normal, and does this always have to be the case? This is a never-ending journey. Don't be complacent with the detections, but there is a stopping point. Every attacker in the world is not going to try to use this one technique, so make sure you're spending your resources in the right places. But yeah, there's lots of places you can go from here, but I'd say be curious, look for opportunities to pivot. And technical limitations sometimes might frustrate you, but it can also lead you to think of detections in a new way. One example of that would be, we're talking about normalization of obfuscation. Well, in one point in my career, I had tool sets that did not allow me to do normalization, which was very frustrating. So what I had to do was a lot of extra work to find different ways of detecting payloads. And what it allowed me to do, less efficiently for the known scenarios, is it allowed our entire team to find payloads in ways that no one else was doing, in places no one else could, because they had written all their logic dependent on a normalization pipeline, but we could do it anywhere and can start to write like snort rules and YAR rules looking for multi-layer base64 encoded substrings, because we were doing the work to expand what the plain text would be. Don't be afraid to try crazy ideas. You might break stuff. I broke some stuff, and I had a great manager that had my back and didn't get me in trouble, but said, be more careful next time, but I like your thinking. Let's keep going in this direction. And so sometimes a bad idea is the very beginning of a new way of looking at finding malicious activity. The last thing I'd say is my cube mate when I was at Mandiant is a guy named Christopher Glyer. And he and I would always turn around in our chairs and we'd say, I wonder how often this would happen. I wonder how often the child process word would be this. And so we said it so much that I started calling them I who questions. I wonder how often. If you think this way, write those questions down. If 10 of those ideas, if 100 of those ideas are bad, the 101st idea could be a killer idea that no one's thought about before. And so an inquisitive mind is really important in the security industry, especially when it comes to detection engineering and detection development. So yeah, closing thoughts. Perfection is the enemy of progress, so don't try to be perfect. Make it incremental progress. And know when to stop, know when to pause, and take notes, because someone else might be able to figure out what you couldn't figure out. That someone else could also be you in the future. Like me a year later can figure out problems I didn't know a year before, and that's happened several times. So research-wise, detection-wise, make notes of what you're doing. Say, I stopped at this point because I had to shift to another project, or I stopped here because I didn't know how to go further, Or I stopped here because I was so freaking mad that I just gave up. A year later, you can come back to those notes and realize, oh, there's the answer right there. I know exactly how to solve this problem. Start with what you know. Learn from your mistakes and share your mistakes. People don't like to share mistakes, but it's a really great way to share information. Failing at something does not mean I am a failure. It means I tried something that didn't work. And failing is the best way that we can actually learn and improve. So share those failings with others. And lastly, I'd say just be a good, kind person. Like, there are a lot of really smart people in the world that have a lot of ego. Like, please try not to be that person. Like, try to be humble, help people, ask questions. Don't make someone feel stupid for asking a question that you think is dumb. Like, we all started from nowhere, and we all got to where we are from the help of others. So try to remember that, help other people along the way. And when you don't know something, just say you don't know. I don't know. I don't have experience in that area. Or I don't know, but I know someone that might. Can I connect you with that person? There's no reason to feel like you're supposed to know everything. When we come to conferences like this, there are so many domains of security that we should celebrate someone who knows an insane amount about Android reversing, even though I know nothing about it. How cool is that? We all work in an industry where we don't have to know everything. If musicians had to know every genre of music, we'd have no music. If I play rock, then I should be able to appreciate jazz music without knowing anything about it, because it's different and we should celebrate that diversity. Always have to recognize the things you learn and where you learn them from. So I always like to give a shout out and a thank you to my manager, Nick Carr, at my current manager now, Ian All, Stephen Miller. He was the guy that has some great blog posts on UR rules, and then Matthew Dunwoody. We all work together at Mandiant and FireEye. We're all at different places now. But definitely a huge thank you and shout out to them, because they've taught me so much about thinking differently about detections. They encouraged me to even start doing research and to start speaking at conferences, and so I'm always appreciative of them. And then lastly, I always like to thank my wife, because it's a huge sacrifice for her for me to spend a lot of time doing research, for traveling here. And so again, just like to say thank you. She will probably not watch this live stream, but if you do, thank you. I love you. And yeah, with that, I'm going to open the floor for questions, but I'm going to end on the last slide, which is the same as the first. So here's my contact information. If you have questions and want to ask online, feel free to message me anytime on Twitter, LinkedIn. And feel free at any point in the conference. I'll be around all day today and tomorrow. I'm an introvert, so I don't go around talking to everyone, but I will talk to anyone who talks to me. I love having conversations. Just be prepared to teach me a new Kazakh word, a Russian word, because I'm trying to learn a little bit while I'm here. So with that, thank you very much for your time.